let me get started here. So I have these questions that I want you to come back to and finish, kind of make a dent in the large group of questions that I added this semester. So this is chapter 5, problem 83. As you can see from the dates, these are the questions you've done 2-3 weeks ago. But I'm basically going to use the rest of the semester to go back to the chapters 1 through 5 questions, kind of in reverse order, and finish up those questions. So let me read this question and answer it. So it says, a force acts on a car of some mass. Okay, let me just start doodling. I'm just making sure that I understand what the question is saying. This is my car, represented as a box with some mass, so that the speed v of the car increases with the position x. Oh, interesting. So they are giving us a speed as a function of position, and it's saying it's going to be kx squared. Interesting. So I don't think I'll be using standard strategy here, and this is a little bit before we formally cover standard strategy. I think I'm using calculus, probably, where k is constant and all quantities are in SI units. Okay, find the force acting on the car as a function of position. Yeah, so as they ask about force, I hope what you are being attentive to is what kinematical quantity force is related to. It's always acceleration. Force and acceleration, they will always be able to give you some information about each other. So, and I said kinematical quantity because that's the information you are given. You are given kinematical information. So I need to think through, how do I get acceleration from here? And if you're thinking of any of the kinematics equations, like, x is equal to x naught plus v naught t plus 1/2 at squared, v is equal to v naught plus at. I hope you very quickly realize that none of these are applicable, because these were the formulas for constant acceleration. Here, the form of this function, one, you're not told that you have constant acceleration. Two, everything in the question should be hinting at that these things are function of position. So acceleration, rather than being constant, it'll be a function of position. So, but through relationship of position to time, it'll be a function of time. So if you are thinking about using kinematics formulas, does not work. So what you have to fall back on are the definitions. Definitions are what's always correct. Kinematics formulas, they were useful when you are working with the constant acceleration problems, which this isn't. So you fall back on the definitions. The definitions say, let me write down the definition for velocity. Velocity is the time derivative of position. In a similar way, acceleration, which I'm trying to find, is the time derivative of velocity. So that's what you need to do. Now, if you might be thinking that, but I don't have velocity as a function of time, I have it as a function of position, then there are some calculus things you can do to work through that. Let me demonstrate. So I'm gonna say my acceleration is the time derivative of the velocity. So I have velocity as a function of time, k x, and let me leave some room, squared. And what you have to remember here is k is constant, but this x here, it's probably gonna be a function of time. Once you recognize then I hope you remember chain rule from calculus. So in taking this derivative with respect to time that you don't have quite function of yet, you can first start by taking the derivative of the outside. So kx squared, derivative of outside, so k is constant, nothing happens. X squared, the function squared, the power rule, 2 comes down, and it's going to be, so 2k x as a function of time raised to power 1, and you are not done. This is where I'm saying you should use chain rule, which says that if you have a function g, which itself is a function of f that is, g function of f, and f itself is a function of a final independent variable, and you're trying to take a derivative of that. Then you take a derivative of g with respect to f, that's what I've done here, and then you multiply it with a function of derivative of f with respect to your final independent variable. So that's what I'm gonna do. I'm gonna write out, I have, that one is gonna be confusing with the prime, so 2kx times the inside derivative of x as a function of time. And you might be thinking, hey, I don't know what that is. Well, let's write it down and see what we can do with it. So this is what we have. We have our acceleration is 2kx times dx dt. And before you give up saying, I don't know dx dt, you do know, because dx dt is velocity. And you do have expression for velocity as a function of x. So you just plug that in. Plugging that in, you get 2kx times that kx squared. Just algebra. Or I think you do something similar when you take like implicit derivatives and all that. But it comes down to, it helps to write it down, even the things you don't know. Then you might be able to recognize that something that you actually know. So simplifying this algebra, I get 2k squared times x to the third power, and that should be the correct answer. Let's try. Oh, wait. That's the acceleration. So if they were asking us for acceleration, that would be the correct answer. They are not asking us for acceleration. They are asking us for force. So force, Newton's second law, it's a mass times acceleration. So we just multiply mass to this whole thing to get to mass times 2k squared times x to the third power. That should be correct, and that's why they told us the mass. We need that to make acceleration into force. So mass times 2k. By the way, how the exact format you put it in, how you simplify, don't simplify, doesn't affect the answer. It's the grading system it uses is it plugs in basically random numbers into these symbols, and as long as the expressions are numerically equivalent, they will get graded as correct. I think answer key itself has probably the simplified version, yeah, but it doesn't matter. You could have even left it in an earlier form that I had that I thought I wanted to simplify. Like you could have left it as this form, like, oops, I guess actually this is the previous form I had, and you can just leave it here, and this would also get graded as correct.